I'm sorry. Now we go on with cable dynamics. We are through with rain wind induced galloping, and we now come to some phenomena which are not dynamic beyond all limits, but which are quasi-static, I say. We have deformations, but they are limited. The first is wake galloping. I must say, I'm not sure whether I would have classified it here under galloping, because what happens, it's basically if two cables are close to one another, say twin cables horizontally, there's horizontal wind, then due to a wake, which is basically vortices which form and which have the right frequency, they act on the second cable. So the cable again gets a small but limited kick, so to say, from vortices which form. I'm not really sure why Kovacs made this galloping. So I just mentioned there is a phenomenon which is real. If we have, especially with the backstay cables, if they are close, we sometimes have to make connections, stiff connections between the two, so they cannot oscillate independently, and with that the phenomenon is solved. So this was just for theoretical completeness of galloping. Now we come with the next 2 points to something like what I call internal resonance. It has basically not to do with wind, as we had for the dynamic excitation, but it has to do with frequencies, movements in between beam, tower, and stay cables. The first is the anchorage excitation, and it's easily understood. Our cables have a sag, and if an anchor point, normally at the beam or at the tower, moves periodically, maybe by wind excitation of the beam or the tower, then we have again the phenomenon of the, say, cloth line with the sag, and if we pull here a little bit in the right frequency, then the thing will oscillate. Very simple. We have all experienced it in some way or another, and naturally this occurs if the frequency of the cable is identical either with the beam or with the tower frequency. It occurs, and so we have to do something against it. These internal resonance or the amplitudes have to do with the different masses involved, which is we have high masses in the beam or in the tower and comparatively small masses in the stay cable. And if we have a not unusual ratio that a deck is 225 times heavier, I say, than a stay cable, then that's not unusual. And then I saw here the formula missing. There should be a square root of this mass ratio. We have to fill it in. So the amplitudes are in the range of the square root of the masses. In this case, conveniently, the figure 225 was chosen because square root of 225, as we all know, is 15, a straight number. So in this case, this little amplitude, the bridge may have, even by traffic excitation, if we have tracks in a certain frequency, will be 15 times increased in the cable amplitude. The ratio, square root from the ratio of the masses, gives the ratio of amplitudes. If we have here an amplitude of 5 millimeters, we will have 75 millimeters square root from in here. So it's not bringing the bridge down, as I told you, but it's a nuisance. And it may cause fatigue problems, so we don't want it. Normally it's not really a problem because the lowest cable frequency and the beam or tower frequencies are different. They are not normally in that ratio that this occurs, but it can from cars or so, from trucks. Also, what may take place is if we have freestanding tower legs. There may be, due to vortices forming, just the vortices from one side to the other, and they exert forces on the tower. And now when the tower starts to swing this way, the cables will swing transversely. That can happen, and so one has to do something against it. You may say, yeah, well, I mean, who's so stupid and making the tower legs like this? That's no good. We rather have an A so they support one another. Yes, but them architects sometimes come up with these, and there are two. One cable-stayed bridge, Vladivostok, Golden Horn, is under construction with towers like this. And the Fehmarn crossing, Baltic Sea crossing, the bridge design also has these towers. I was involved in both. I wasn't quite happy. I told them from the beginning, listen, we have vibration problems. We'll put some dampers in, good enough. So, okay, you can do it. But from a dynamic point of view, it's not a good solution. And in fact, there are dampers provided in both cases. And I always think a damper, we'd rather design bridges which do not require damping, if possible. There is another phenomenon which is more difficult to understand, I felt. And that has to do it is active also on a vertical cable. Now, with the anchorage excitation, we thought about an inclined cable with a sag, and we pull it and the sag goes in and out. We understand. Now, if I have a vertical cable and I pull it, where's the phenomenon to get that excited? Well, there is another possibility of parametric exciting of a stay cable if we vary in the first eigenfrequency a parameter which determines the eigenfrequency. I told you eigenfrequency, square root of cable force, and 1 divided by length. So practically what we can do is we can vary the cable force. And if we have a vertical cable and we pull it with double the eigenfrequency, then after some time the cable will oscillate transversely. Just believe it, know it, it is there. I'm not aware that this really has been a problem with cable-stayed bridges, but parametric excitation, double the frequency, a vertical cable will oscillate transversely. Just keep it in mind. Of course, it also works for an inclined cable but it's not by taking out the sag, it's by changing the cable force due to vibrations. It's theoretically fully distinct. Practically, I think it's hard to distinguish. Now, the final phenomenon is if we have turbulent wind, which has the turbulences in random frequencies. Then we know if a turbulence hits a cable, it's like a load, the cable will deform a little bit and then comes back. And now, statistically, we can find that from these random turbulences, there will always a few be just in phase. Say 50 or 20 will be at random and they will not do much harm to the cable. But from these 20, 2 or 3 will just hit in resonance when the cable is just out or back, and so on. And so from this, say, random resonancy, we get a certain excitement of the cable, and with real-time statistical methods generating some random wind and so on, one can mathematically show what it would mean. And we had this phenomenon of the Helgeland Bridge, which we mentioned and I will show you later in some detail in Norway, which had extremely high winds, very high storms, plus the wind came over a series of mountains, I remember, called the Seven Sisters. And because of that, it was very high, it was a high turbulence, 25%, which is very much, otherwise 5 or 10. And Kovac, when he saw the wind characteristics, oh, listen, careful. And he calculated all that, and we found out that the wind, the turbulent wind on bridge and cables, with some turbulences hitting by chance, statistically, in the eigenfrequencies, was an important loading. It actually was the loading which governed the design of the bridge beam in transverse direction, because it increased the already high static wind loads from 70 meters per second wind we had there. There was a certain dynamic factor, if you want to, which we had to apply, I think 1.4, 1.5, to increase the basic static load. And for this flimsy bridge in this high wind, this was a governing loading. So if we have very bad wind climate, high turbulence, just the buffeting of the wind, of the turbulences against the wind statistically can give us problems. Now we have then the vortex shedding, which is a very general phenomenon, which we can also see on lampposts or cooling towers even. There are vortices forming, von Karman vortices, which shed one side, the other side, and by that exert transverse forces, and governed by the so-called Struhal number, the shedding frequency, if that falls together with the eigenfrequency of the cable, of the lamppost, then there are small but constant forces, acting on the structure and cause vibrations. I've seen it several times on lampposts, vertical lampposts in wind, and when you put your hand on, you could, or even stronger, see it. It is a well-known phenomenon where those collapses of circular tanks, silos, where Mr. Scruton, a famous British aerodynamic man, found the so-called Scruton helix, where he took a steel profile around a large tank, and by that broke the helix, broke the vortices up, Scruton helix. So it's a phenomenon well known, but only in exceptional cases dangerous. Now, we are through the various excitation phenomena. What to do about it? I'm just going one step ahead, not just the cable excitations, but the whole bridge vibrations. In the early times of suspension bridges, long span bridges, was the one and main cause bringing bridges down. We'll have it in the overall dynamics later on. So this phenomenon was known since a long time, but people couldn't make head or tail out of it. Only since we understand the mechanism can mathematically formulate it. And then we can also define a damping at what place, what size, which will suppress it. And since we can do that, the real danger is out. We are not too optimistic that we now can calculate everything in advance. Some things are quite clear, something has to be done, and we install dampers or things like that in before. Sometimes it's not clear. And then it's not bad to say, okay, we are prepared if the cables oscillate. So we install already anchorage points for dampers or tie downs or whatever, and we just wait and see. Maybe nothing happens. That's not a bad politics, but at least you should prepare, say, the anchor points, even if you say, well, I don't know. That as a general politics on damping, because these dampers are expensive and they can be maintenance prone, so you have to do a lot about it. So they are, over the life of the bridge, they are expensive. Okay, now damping has to be applied to the cables at a certain distance from the anchorage tower as well. Can be done as beam. Normally we do it at the beam, we can better inspect it and all that. But if necessary, and it has been done, can be done for two. And the damper we can normally calculate as a plastic system and an elastic spring. And very important is the distance, and the maximum damping we can apply depends on this delta L by L, and that normally comes to 2 point some fractions percent of the whole length. So if we have a 100-meter long cable, we should have something like 2 meters away from the anchorage and so on. Now this is of certain importance because I have to make a transverse support here, or I have a stiff steel pipe or something. So I don't want to have that too long, but the distance where I place it is important, about 2% of the length. And now it started with hydraulic dampers. I remember the Breton Bridge in France across the Seine River. I think it's from the Breton, but they look the same for others. They had these, and these are just shock absorbers. So they started out with standard car shock absorbers, where we have a fluid running around pistons, or pistons run through the fluid, and by squeezing this hydraulic fluid through the tiny part around, work is done. They are heated up, and that's how energy is destroyed. So shock absorbers from cars, the same here during construction, I think it was, cable exchange of the Kuliah Bridge. There are other examples. A certain shortcoming of these is that because as I used to say, bridge cables are a little nervous. They are always in very small vibrations. You put your hand on, you will find they are not still. It's not meters, but they are nervous. And now this is just pure poison for the seals inside a hydraulic damper, that you have these permanent, very small movements. And so the result was that these always had to be exchanged after about 1 year, because the O-rings seals were destroyed. So there was a little shortcoming. Of course, there were better dampers being built and so on. There were then, for Normandy Bridge, for example, first, later Rion and Tyrion, which I've shown you and we will see later in detail next semester. This rather primitive car shock absorber business I showed you here has then been refined into some hidden, and a layman will not see that this is a hydraulic damper which is inside here with lever arms and things like that. But it's the same principle, hydraulic dampers. Those were what I call outside or external hydraulic dampers. There is a principally other idea which I compare with the motor for cars. Our standard has vertically up and down going pistons. And there was this certain inventor, German named Wankel, who had a rotating cylinder. And that's the same here. We have inside here a rotating cylinder which is externally supported in the center. So when it rotates, these chambers change in thickness, so to say, from, I don't know, 5 millimeters to 25 here. Just think externally supported, rotating, then this point where it's closest to the outside of the cylinder rotates around here. That means in this way the fluid has to be squeezed around like in a Wankel motor. The chambers are going around. So that's an, I would say, elegant solution. However, there's something better which Kovac, I'm not saying he has invented it, but he's very much in favor. He always uses friction dampers. Now, a friction damper is basically the principle of disc brakes in a car. We have, so to say, two discs, and we press them against one another, and there is a high friction surface which in a car breaks the speed by exerting friction on the axles. And the same is here. These two, when they work against one another, one is externally supported, one on the cable. Again, friction work takes place, it warms up, and by that work energy is destroyed, which is damping. And it's a little difficult going into, but the thing is, if this would be the required damping level for galloping, which we take as an example for cables, then we have, first of all, a certain eigendamping of the cable. You remember logarithmic decrement, 0.01, something like that I showed you. This is a delta and this is the amplitude cable. You need a minimum movement of the cable, otherwise to get the friction started. Otherwise it's just fixed, it doesn't work. And when you have this, during that time you have only the eigen damping of the cable itself. Then very quickly, from a certain starting amplitude movement of the cable, This, in addition to the eigendamping, there is the damping from the friction. So here we are high up, this damping for galloping required to suppress galloping. And later on, for very high amplitudes, the friction again goes down. But this branch will not take place because if we have a total damping so much above the required damping, the amplitudes will very soon go back here and decay. So this branch is of interest. After we have reached a certain minimum amplitude, then they start to slide against one another, and the friction is activated, and this work is the damping which reduces the oscillations. It's a more elegant solution, and it's not so maintenance prone. These disc brakes go on for a very long time. We have one other phenomenon here. Let me go back a few. And that is, I've told you the friction is proportional to this distance, delta L. Okay, beautiful. Now we increase that as long as we can and have a good high friction. Yes, sir, but at the same time now, we have longitudinal movements of the cable, strain, small, but still, if over several meters added up, it comes to a few millimeters from these oscillation phenomena. And that means we have here small movement, few millimeters, but it's there. And so that has to be taken into account. We cannot make this rigid between the cable, which has longitudinal movement, and the outside, maybe a steel pipe or something. And now there are various ways to do it. I just give an example. VSL uses elastic plates to take up the relative movement longitudinal between stay cable and support, whatever that may be. And well, okay, here we see naturally how beautifully these dampers work. BVR has a completely different story for taking up the longitudinal movement. Again, you remember, the further we are away, the more effective the damper becomes. However, the bigger the relative movement becomes. Both goes. There's no such thing like a free lunch. We've got to pay for some advantage with some other. And so they have a very intricate, these are the brakes in here, mechanical mechanism. I've seen a model of that, which looks very nicely. So it's not elastic there like Freycinet, but it's a mechanical hinged system which can take up these little movements. So there are all things under preparation. And in development, the big cable fabricators, VSL, Freycinet, Shinko, BVR, I hope I haven't forgotten one. They are constantly developing their systems, and it's interesting to find out what is the latest. There's a third possibility. We had hydraulic dampers with a fluid squeezed through tight places. We had the friction dampers with disc brakes. And the third is elastomeric dampers, which very simply is that we support the stay cable, say at the tip of the steel pipe with this neoprene ring, I normally call it. Instead of the neoprene, we use an elastomeric which has internal friction characteristics. So it's not just elastically deformed by the cable oscillations, up and back, but by this elastic deformation, energy is dissipated. Well, you know, I'm not sure. Hysteresis curve like this is the reason. So just remember there's a rubber with internal damping characteristics which takes up energy, and thereby also for small cables it works, can be used. There's another shape, again from Freycinet. They call it Diabolo, where the stay cable is supported within a steel pipe, and when it oscillates, then this is squeezed or the other one is squeezed, the support, and by squeezing them there is an internal friction, so to say, within the elastomeric which which consumes energy, internal work. Non-elastic. Elastic work doesn't consume energy. That's why we need sort of plastic dampers, elastic. There are no elastic dampers. That's impossible. Now, I mentioned before, this was once we have the cable, so to say, installed and the thing is vibrating, what to do? Various 3 types of dampers. However, much more clever naturally is, instead of damping the oscillations, try to avoid them from the beginning. And that can be done by preventing the forming of these rivulets, as I was talking about in wind-rain induced oscillations. And we are talking mainly, the whole thing here is on wind-rain induced vibrations, I told you. They are catastrophic. They can destroy or really damage stay cables. All the others are a nuisance and we have to suppress them, but they're not really bad. So we go to great lengths to prevent the cause of rain-wind induced oscillations, which are these rivulets, which I told you, these little rivers from raindrops on the top left and bottom right, if the wind comes from the left, and they oscillate a little bit. If we prevent that they form, there is no wind-rain induced vibrations. And what are the possibilities? Well, we have the dimples, and I told you in the beginning how important for large bridges the wind on the cables is for the bridge itself. So we must be careful that if we change the surface here, that we do not get, on the other hand, bigger wind loads on the bridge. No good. So, and I also showed you that these different profiling of the surface reduces actually the drag factors. So we kill 2 birds with 1 stone, if we want to say so. Again, dimples, you know, from golf balls. We have here longitudinal protrusions, I call it. They can be put on easily in the manufacturing process. And the third are helices. I told you about the Scruton helix, which he found for big tanks around to prevent them from vortex shedding. And that's the same. And they are normally, these are, I think, or can be, like welds, that there is a plastic small bar which is heated and then during processing is put on. And these 3 have been used for various bridges. Tatara was world record, Normandy was world record, and Higashikobe is one of the major in Japan. So they have been tried and they work. Again, test what happens if we have a pipe in laboratory, low wind speed, low rain, and we have the rain-wind induced oscillations. Well, we have amplitudes, again, 7 to 15 meters per second wind, medium wind, and here are the amplitudes. We have these high amplitudes for about 10, 12 meters per second. If we put, however, just these helices on, as shown here, the amplitudes go down considerably. So the same effect, at least under this point of view, there are others, we reach with more expensive and complicated dampers, we can achieve by just putting on these simple helices. Interesting, isn't it? Now, the last thing we can use is cross ties, which are either they go here to the tower, normally they go rectangular to the cables. Has been done, and it's quite obvious. I mean, these cables vibrate beautifully, tie them down. Here we go, problem solved. Yes, in a way, first of all, we must be aware these are, say, strands. So they act elastic. There is no damping or energy consumption. What we do is not damping the cables, but we change their eigenfrequency. Because by tying them down, we install here, I would say, a sort of elastic support. Over the length of the bridge, some elastic supports. That means the frequency is pushed up. So basically that's what we do here, and it can be very helpful against internal resonance, where the cable amplitude, cable frequency is close to bridge frequency. There are, I would say, two disadvantages. The one disadvantage is optical. It doesn't look nice. I think I'll show you later for the Helgeland Bridge in Norway, which I think is a very nice bridge. I always use the pictures directly after the end of construction where those ties were not installed. Because with the ties it doesn't look as nice, and there are other examples. The second is it makes it rather difficult to inspect the cables with cars, small cars running up the cables for inspection trolleys. I've shown you some in the cable lecture. Of course, there are theoretical ways you can hook them in and out, and it's all not very good. So these tie downs I would avoid if possible at all, because, as I say, they don't look nice, and in addition they hinder easy inspection and maintenance by little trolleys running on the stay cable. These are pictures from the installation of these transverse stays of the Normandy Bridge. It was done by free climbers, of course, secured with ropes and all that, but you see there was no scaffolding or something like that. They climbed up and connected them, quite interesting. And they say here, provide the fix point along stay cable. The fix is what I told you. It's elastic support, it's not a fixed support. Very long stays for parametric instability. You know what parametric instability is since today? Internal pulling at the stay cables. And they did a lot they did a lot for investigation there. That was the first time it was really said. By the way, it's interesting to note that the English word for bridge inspecting with, say, mountain climbing equipment is Abseiltechnik. They use the German word, it's quite, for bridge inspection or so, it's called Abseiltechnik. Okay. Now, to sum it up, I think the movies have shown to you what an important and detrimental phenomenon stay cable oscillations can be. So we have to take them serious, and we have, during design, try to find out whether there is a high probability that they will occur. In that case, we have to install some dampers, or if there is at least a danger, then we will prepare for later installation of certain types of dampers. We've gone through the dynamic excitation phenomena of stay cables. The one overriding concern is galloping, especially rain, wind-induced galloping, because that pulls constantly energy out of the airflow. And so the amplitudes can grow theoretically beyond all limits. They can be very damaging, and so we have to be careful to avoid them. There are other wind-induced phenomena like buffeting and vortex shedding and things like that, but they are of limited amplitude. We must watch them, but they are not as dangerous as the rain-wind induced vibrations. For avoiding these vibrations, there is the most elegant solution, I call it, by profiling the surfaces so that the cables, the wind cannot attack the cables the way he likes for, say, rain, wind, and induced oscillations. Or if that doesn't work, it's impossible, we can dampen, we can calculate the required logarithmic decrement. You now know what that is, huh? We can calculate the necessary additional damping in addition to the eigendamping. We can use hydraulic dampers, we can use friction dampers, and we can use elastomeric with an inner damping factor. So with that, I think I've given you a fair picture, at least of the problems. You will not be able to do the calculations and to solve them, but it should enable you to understand what are the problems, when to go to a specialist, and then to be able to understand the report of a specialist. Thank you.